Okay, here we are. We're grading an FRQ. This is going to be interesting. You've already taken this FRQ, and now you want to find out how you answer it and how the points end up arranging. By now, you've got your scoring guide where we'll identify the points that we have. So you can have that scoring guide next to you and your own FRQ in front of you and see how things go along. Now, I'll give you a few tips as we move along. First of all, naturally, this is one of the first three questions on an FRQ. They're all worth 10 points. Each one is worth 10 points. So that sort of lets you say, okay, answering this question is 10% of the AP exam. So it's worth the 22 minutes that you should spend on it. So here we go. We're going to start with this compound. It's called carbamic acid, and you've never seen it before. And I'm sure none of the other AP students taking this exam would have seen it before either. That's typical. On AP, they'll end up giving you something new, and you know what you will need to answer this. It's just that you have to apply it. Now let's see. Carbamic acid is an unstable compound that spontaneously decomposes into ammonia and carbon dioxide. The skeletal structure of the molecule is shown in the box below. Okay. 1. Or I. Complete the Lewis electron dot diagram. Hey, you know Lewis electron dot diagrams. For the molecule in the box below, include any lone pairs of electrons. So we're going to have to make sure we show any lone pairs of electrons. And your structure should minimize the formal charges. Okay, if you're doing a Lewis dot structure, you know you're going to be doing valence electrons. So we're going to have to figure out the valence electrons of NHCO. Okay, now I hope you've already memorized those so that you don't have to end up flipping to a periodic table. But if you have to, you can just pull out your, flip over to the periodic table and do your count. First column is 1 valence electron. Second column, no matter who is in here, is 3 valence electrons, 4 valence, 5, 6, and 7. And that's it. That's our, doesn't matter whether it's nitrogen or phosphorus, it's going to be 1, 2, 3, 4, 5. Nitrogen, 5 valence electrons. So let's start with the formula. Nitrogen, 5 valence electrons. With this VE, they'll know what we're writing about. The rater will at least. Next, we've got hydrogens. Now, the formula is H2, but there's an H here, 3, so there's 3 hydrogens. So that's going to be 3 valence electrons, 8 so far. Now, we've got a carbon. Now, remember, carbon was 4 valence electrons, 1 less than nitrogen. Don't mix the atomic number up with the valence electrons. And then finally here with our oxygen, which we've used a lot, as 6 valence electrons, 1 more than nitrogen. So let's do some addition. 8. Oh, but wait a second. There's 2 of them. So cross that out. 12 valence electrons. Yeah, 1, 2. Okay, 8 plus 4 is 12, plus another 12, doubling 12, 24 valence electrons. Now, I would do a double check, because if you got this number wrong, you're in trouble. Nitrogen, yep, there's only 1 of them. 3 hydrogens, yeah, 3 electrons. Carbon, 4 valence electrons, that's one you should memorize. And 2 oxygens, 12, 24. Okay, that's it. That's our first step whenever we're doing a Lewis electron dot diagram. Next step that we follow in all our things is we put our bonds in. I'm going to draw them as lines. 2, 4, 6, 8, 10, 12. You could put in dots if you preferred. It's easier and faster for me to use these. I'll count again. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. That takes care of 12 electrons, leaving us behind with 12 extra electrons that we put onto our surrounding atoms. And that's what we're going to do right here. Now, here's our center atom. We've got 12 electrons that we're going to put on the surroundings. Now, here we've got nitrogen has 2, 4, 6. It needs 2 more electrons to get its octet. Oxygen here has 2, 4, 6, 8. There's an octet. Here's our other surrounding oxygen. 2, 4, 6, 8. Hydrogens are all set. So we're, oh, wait a second. 2, 4, 6, 8, 10, 12. We've used up 12 electrons. There aren't any left. And look, lo and behold, our poor carbon does not have its octet. And only aluminum and boron can survive without an octet at least. So we know we're going to have to put a double bond in. And this is where the formal charge comes in. Which pair of electrons do we slide over to end up doing that double bond? A sharp student would have read this and said, this is an acid. And we've done acids a lot, and you know acids are carbon, double bond, oxygen, OH. Cool. They're cool. You've done them often enough, so you know this single oxygen uses its pair of electrons to get our octet around the carbon. That would be a fast way of figuring out the right way of doing this. Now you could end up going the formula charge route, which is longer and it takes more time. You should be acquainted with it, but in this case, you don't have to use it. Now, sometimes if you're taking too long, you're doing it wrong. This hint up here, carefully reading, will help you with that. Now, I'm going to go over the formal charge. You can look it over in the answer, our solution sheet that I've given you. But here we've got nitrogen. It controls 1, 2, 3, 4, 5 valence electrons. That's exactly what you'd expect. Here we've got oxygen, 1, 2, 3, 4, 5, 6. It's controlling 6, which is what oxygen does. And the same thing here. But again, that would be the long way of solving this. Okay, let's see. How are we running on points on this? I'm going to pull out the sheet where you're going to tally your own score. And here for A, Lewis dots, you get 1 point for having the right number of valence electrons and bonds. And if you put a double on the wrong spot, no big deal, you still get that 1 point. Then you get 1 point for the double bond. Okay, that was worth 2 points. Very nice. 2 points available for a typical problem like this. Now, next. Based on your completed diagram above, what is the expected oxygen-carbon-oxygen bond? Okay, so here we've got our carbon. And our carbon has 3 domains. Now, in this diagram, it looks like it's 90 degrees. But we know these diagrams, these skeletal structures, don't really give you the right angles. We know that if we have 3 domains, that we end up separating those domains, we don't count pi bonds, by 120 degrees. So that is our carbon, carbon, right here, 120, that's it. Fast enough, but you've got to know your domains and know about pi bonds. Let's see, that was I, and you end up getting a point for 120 degrees. 3 points so far. That's probably passing on this exam. You probably would end up getting a passing grade by doing 30% of these FRQs. The average correct number on most FRQs is 3.2, 3.5. Next, identify the hybridization of the nitrogen in the molecule. Okay, read carefully. Very, very common mistake here that the graders indicated was that people took and gave the hybridization of the carbon, not the nitrogen. They rushed, they had just on the carbon, said, oh yeah, I know carbon's 120, so I know that's an SP2 hybrid, and they put that down. They're asking for the nitrogen, which sort of makes sense because they wanted to see if you knew a different molecule. So that nitrogen has 1, 2, 3, 4 domains. So we need 4 orbitals around it, and the only way you can get 4 orbitals is to use a sp3. An one s orbital combined with 3 p orbitals gives us 4 domains. Each one of these is an sp3 orbital. hybridization of that carbon is sp3 hybrid because it's got 4 domains around it. And again, reread the question. Identify the hybridization of nitrogen. And we got it. Okay, let's pull out. Here we go. 4 points out of 10. That's most certainly at least a 3. So you could close your book and say, okay, I passed the exam just with those, but we can do better. We can do better. So let's go on to the next question, B. Okay, now we're here at B, and this is the mathematical part of this problem. And I've got my calculator here, so I'm ready to go. Now, they'll switch topics very quickly within these first 3 questions. So expect to switch thinking hats on this. The bond energy of a nitrogen-hydrogen bond is 460 kilojoules per mole. Okay, that bond energy is the energy needed to break a bond. That's 460. I'll write that down right now because that's going to be an important value, I bet. On analyzing the compound using infrared radiation, okay, we know IR is a low photon energy radiation compared to visible and ultraviolet. And if you remember, it doesn't break bonds. The photons don't have enough energy to do that. It is found that the nitrogen-hydrogen bond stretches on absorbing a photon with a wavelength of 2,860 nanometers. Yeah, a little photon hits this and it stretches. Now let's see, what's the question? What is the amount of energy absorbed in stretching of a single NH bond? Well, absorbing a photon stretches it. So we've got to find the energy of a photon of this IR light. Well, we've done that multiple times. I mean, that's one of the reasons I put those questions on the Web of Science. You're going to need your equation, which I hope you've memorized, but if you haven't, you go to the equation sheet and say, okay, here it is, C equals lambda nu. That will give us the frequency, because you'll need the frequency to get the energy. So, speed of light is equal to the wavelength times the frequency. We need to find the frequency. The speed of light, I remember, and you probably should remember, 3 significant digits, is 3 times 10 to the 8th meter per second. That's like the universal constant. I mean, you could use the value they've got in the book, in the equation sheet, which is 2.998, but 3 sig digs is going to be enough. Our wavelength is 2,860. Now, I'm not going to write nanometers because this is in meters, and I'm not going to mix nanometers and meters. So I'm going to write down times 10 to the negative 9, which is what nano stands for, meters, times our new frequency. Okay, frequency, calculator time. Now, even before I do the calculator, I've got to realize that frequencies are going to be high. You're going to get a big number. It's got to be a big number because you've got billions of a meter waves going by at the speed of light. So I'm going to take my 3, second function, E, 8. Yeah, big number. Divided by 2,860. I'm going to double check. It's easy to flip numbers around. 2,680. No, this is 2,860 nanometers. Nano is second function, E, negative 9. Very, very small. 10 to the negative 9. Enter. Okay, frequency is 1.05. Don't carry out all the, please don't write all these numbers out. You're going to waste your time and you're going to embarrass me. So, 1.05 times 10 to the 14 per second. The meter's canceled. That's a big number. Yeah, you're going to get billions and billions of photons going by you every second. That makes sense. Okay, now next step, once we've got the frequency, we we can find the energy. Energy is equal to Planck's constant times our frequency. Planck's constant, you can look it up. That's the one that's tough to memorize. This is not a nice, easy number. 6.63, and again, I can do it, or you can carry it out to the 4 digs if you like. 6.63 times 10 to the negative 34 joule seconds. Now I'm going to double check that. Yep, number is correct. You don't want to get this one messed up. You know, not putting that negative there will mess you up. Putting a 35 there. No, that's right. Spend the time to make sure that you're putting in the right numbers. Now, I'm not going to bother rewriting the frequency because I've got that on my calculator already. Okay, I'm going to take that frequency times, and I'm going to be careful, 6.63 times 10 to the negative 34. Now, we know we're going to get a real small value because the energy of a single photon, I mean, that's the smallest piece of energy you can get from a wavelength, is going to be really, 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 really tiny. So what's our answer? Yep, that's a tiny number. The negative 20 is a tiny number. My energy is going to be 6.95. I'll carry it to 3 significant digits. Times 10 to the negative 20. Now you're going to have the unit here. Joules for that photon. And double check. What is the amount of energy absorbed in the stretching of a single NH bond? Did I answer that? Yeah. Wavelength, this is it. Now let's see how many points I get on that. We'll pull out our little thing here, and just as you might have expected, they're going to give you 2 points because this is an involved calculation. So now let's see, we've got 1, 2, 3, 4, plus 4, 6. Okay, that's going to be a 4 probably. 60% is pretty typically a 4 on FRQ questions. So there we go. We're moving along very, very nicely. One thing that you could have done is you could have used the equation where you derive yourself, where you say the energy is going to be equal to, in case you like to have your own equations, that where you've got hc divided by lambda. And if you would have shown this, you would have gotten your 2 points because you had everything set up. If you set the equation up like this and then did the calculation in one fell swoop, then you would have gotten the 2 points anyway. But you have to show your calculations. You don't show the calculations, even though the answer is perfect, right, sig, digs, and everything else, you lose it all. They figure you copied. So you must show your work. Now, let's answer the last part of B. Would increasing the intensity, the number of photons of IR radiation break the nitrogen-hydrogen bond? Well, first of all, IR doesn't break bonds. So the answer is going to be no. So I've answered that question, but they're not going to give me the point for that because they say explain your answer. There's a couple of ways. You could say that IR radiation has a longer wavelength, and photons of that wavelength cannot break strong bonds like these, and you probably get the point. What I would do is I would just do one calculation. I would take the energy of the photon, 6.95 times 10 to the negative 20 joules per photon, and multiply by Avogadro's number, 6.02 times 10 to the 23 per mole. And well, in this case we're talking about photons. And I'll just take my calculator where I still have my previous answer. Don't clear your previous answers because you're going to be using them. Times 6.0. That one you should not have to look up. That's times 10 to the 23. Let's see what we got. Yep. 6.02 times 10 to the 23 energy per joules. Here, let me pull that out. There, you can see it better. Enter. Our answer is in joules. But that's a big number, and we always change big number joules into kilojoules. Divided by 1,000. Kilo is 1,000. Okay. IR equals 42 kilojoules per mole. That is, all we got to do is say it's less than the binding energy, which was 460 kilojoules per mole. Not enough. I like the mathematical method. That way there is no ambiguity and so forth. So there we go. Let's get that point. Let's get that point. No, insufficient energy of the photons. 1.1234677. That's definitely 4 territory. In fact, on some tough tests, that's going to be like 5. So again, you could hand in a paper right now and say, okay, I passed. Okay, now on to our last question. Here's our last question, C. It's pretty typical for the questions 1, 2, 3. A little grueling. I mean, these things take about 22 minutes to answer. But the AP exam is a tough one, and if you've gotten up to C and you're pretty certain about the other questions, this is like going to be saying, I've got this taken care of. So, and very often C is a little bit easier than the rest. Let's read it. The complete photoelectron spectrum, okay, there it is, of the element nitrogen is represented below. Peak X in the spectrum, that's this right here, corresponds to the binding energy of the electrons in a certain orbital of nitrogen atoms. The electrons in this orbital of nitrogen have a binding energy of 39.7 megajoules per mole. Yeah, I'm looking at my graph here. Here's 10, here's 100, and it increases here. So this is about 40. It's a logarithmic scale rather than a linear one. So the 4 is stretched out there. While the electrons in the same orbital of carbon atoms, so they're switching to carbon, have a binding energy of about 29 kilojoules per mole. Okay, that's less. Smaller binding energy. Okay, fine. They're telling us that. Okay, I. Identify the orbital and explain the difference between binding energies in terms of Coulombic forces. Okay, now peak X, this is the orbitals for nitrogen. Let's see what nitrogen is in terms of orbitals. I'll pull out our periodic table. Okay, this is the S, and here's our P1, P2, P3. Okay, we've got 7 protons and 7 electrons. This isn't valence electrons. This is the full orbital arrangement. So we know our nitrogen, again, our electron configuration, 1s2, 2s2, 2p, let's double check that again, 1, 2, 3. Okay, 2p3. Now the electron configuration, the PS, mimics your electron configurations. So this has got to be the 1s2. This has got to be the 2s2, and this has got to be the 2p3. Now, does that make sense? Let's look here. Yeah, this peak is 1, 2 electrons tall, and it's a 1s2. It's the one closest into the atom because we have our nucleus here. Here's our nucleus with 7 protons pulling in, and there we have our 1s2. Okay, that fits. Okay, so identify the orbital. The orbital is a 1s. You could say, if you want, you can put the 2, but they just wanted the orbital. It's the 1s orbital. That's what we've got. That's probably a point right there. And explain the difference between the binding energies in terms of Coulombic forces. The bonding energy for this 1s orbital is 40 megajoules. Carbon is 1s2, 2s2. It's got one less electron, which makes it 2p2. And here we had 7 protons, and here we've got 6 protons. Binding energy is 29 megajoules. Oh. Protons attract the electrons with Coulombic forces. That's our electrostatic attractions. Nitrogen has one more proton than carbon, and the orbitals are the same energy level. That explains one more proton has a greater attraction. The grader would be looking to see if you saw that there was a difference in number of protons, and you indicated that the greater number of protons has a greater attraction. That's the only two things they'd be looking for. And don't worry, they're very, very good at reading. I mean, if one person can't read it, they'll pass it off to somebody else to try and read it. So let's see what we've got here. We get the 1s orbital, and n has a greater number of protons. Voila, 2 points. That gets you 9 out of 10. There never has been an AP exam where 90% was not a 5. So this is it. This is good. Let's see if we get a perfect paper. A perfect paper that one student out of 160,000 taking the test will end up getting. Maybe you'll make that. Peak Y corresponds to the electrons in certain orbitals of nitrogen atoms. Okay, here's peak Y. Okay, we know what that one is. That's our 2p3. On the spectrum shown, carefully draw the peak that would correspond to the same orbitals of carbon atoms. Okay, that's the 2p orbitals of carbon. There's only 2 electrons, so we know that 2p is going to be a little bit shorter. And because it has 6 protons, less energy. Now be careful. Greater goes from right to left. So it's going to be here. There's going to be less attraction. So this carbon is going to be somewhere around here. Instead of 1 kilojoule, like maybe 0.8, 0.9. So I would draw that graph here, but I wouldn't draw it 3 high, I would draw it 2 high. This is the carbon 2p2. Double check. Height is right, lower energy. There's my answer. Perfect paper. Very, 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 very rare. Okay, that's it. We've got these. Grade your own paper, and you can find out. Use the scoring guide that I've given you, the written one, and they'll give you some other alternatives and a further explanation of things. Okay, that's it. Goodbye.